Sure.
Okay. Hey, welcome to today's class. Let me open the slides. Let me actually share my screen. Okay. So before we do the syllabus, I think I got an interesting email from Chun. I think I see it here. It is. So he seemed to have done some independent project, which is great. So he tried to work on capture recognition with TensorFlow. So you can see my email, right? I guess. Okay. So capture is basically image-based recognition, right? So he says first part is to generate images, second part is to use TensorFlow to train the model. TensorFlow is, by the way, very popular for deep learning. Now let's see. He says it took him very long, and he seemed to have run it on AWS instance, EC2 cluster. Is there any ways I can shorten the time and then? Okay, another thing is apparently his Jupyter notebook. Oops. I think so. The process exceeded the limitation of the Jupyter notebook. I couldn't register the model to do a test. Okay, so that was probably a memory kind of an issue. What can I do to finish the problem? Okay. So let me open. By the way, do you know what model you ran, like the name of the model or anything like that?
So you mean the model, the name of the model?
Yeah, like what kind of a model, like what technique by chance? Was it like deep learning?
CNN.
CNN?
Yes.
Okay, convolutional neural networks. Okay, yeah, that's very popular architecture for image data or computer vision, so that makes sense. So a couple things on your Jupyter notebook, your second issue where the process exceeded the limitation. So you mean the memory, right? The memory limit?
Yes, it didn't show any other process once it's beyond like 8,000 or 10,000. I can't remember that.
Right, yes. So that actually is a good point. It happens to me as well once in a while. So there are two ways to launch your Anaconda. One is you literally open the Anaconda, right? And then you launch your Jupyter notebook by hitting the launch button on the GUI. Is that how you launched your notebook?
Yes.
Yeah, so that's a standard way. But if you have these memory issues, one thing you can do is open your terminal. Are you in a Windows or a Mac?
A Mac.
Yeah, so open your terminal, and then I will send you this command. It's still in my history, so that's how I pulled it up again. So there's this command where you can put in a limit of a very large number.
Okay.
It will allow for as much as possible. Even then, if it exceeds, then it's an issue with the fact that your Mac cannot handle it and it needs to be run in a different way. But since you're running it through the notebook on an EC2 cluster, is that correct? Or did you run two instances?
Yeah, EC2.
Okay, through your notebook. So then it should be okay. So it's just like some communication related stuff, right? So I pub data rate limit. So that's the amount. So if you put a very large number like this, it should work. So what I'll do is I'll reply it here. Okay. Let me know if it still persists, then we can dig deeper. And then, okay, your code, it's cool. I will go through your code. Is this all, yeah, so this is a, so which is the main file?
It would be the train.
Okay.
Train and predict.
Yes. This is generating the images, I guess. Okay.
Yes.
Yeah, I will go through this. I need to look at it like a little more with more focus. So I will do that. I'll get back to you.
Okay. Thank you.
Yeah. And then we can see about the first one. There are many ways to speed up, but let's start there. Okay. Now coming to our course. I'll do the same thing. Open the syllabus file. Be doing So we did neural networks last time. Is that correct?
Yes.
Okay, yeah. All right, so we did this. Okay. I'm sorry. I kind of forgot if we did this or not because of the multiple classes I'm running. So do you remember if you did the
No.
No,
So
we didn't.
we didn't do this. Even question, I think we skipped one of these. Decision trees we can. Random forest also not done, right? Week 5.
possible? Yeah, we did SVM. Then we did 4. Then we did 3, and then jump to 6, I guess.
Correct. Yeah, 5 also missing. I correct.
Okay. So yeah. So then in that case, you know what? So we could do. I think we should be doing week 7 and then we can jump to the technique. Because for now, once you have some techniques in your hand, which is SVM and neural networks, this is how you evaluate any popular machine learning technique. And even like a lot of people who are just like MBA candidates in big companies understand these metrics, at least to some extent. So this is very popular. So this is how you communicate how your metric is performing or how you evaluate your technique. These are some interesting metrics. So I think we should be covering this. And then we can jump to the technique after that. Okay, so you know what I will do? I will open up something. Give me a second. Let me stop sharing my screen. Okay. Back to share screen. Everyone. Okay, so these are the slides we would be using. These are outside the NumoDocs format, so these are available publicly. These are from university courses. So we'd be doing this once in a while for a few slides. For some topics, we'd be going out of our NumoDocs format, but I think we'd be converting into the NumoDocs format soon. But I do this because sometimes I find some slideshows which are like perfect to what I want to share. So in that case, we rather share it. Similar to like neural networks, we did the Andrew Ng's course material because it's very popular anyway for a starter slide. So these would be the goals of our lecture. So it's all about evaluating measures. So some of these things you might have already heard of some terms, so we would be focusing less time on that. For example, training and test sets, what cross-validation means. So what we'd be covering a greater amount of time would be on these topics: confusion matrices, different metrics that you get from confusion matrices, like true positives, true negative, false negative. Then ROC curves are very important as well. If I did say an ROC on my laptop, it will keep showing some curve or the other because this is a very popular part of someone who does, part of the timeline of anyone who does machine learning. I'm sure they will keep generating a lot of ROC curves into their workflow. Okay, so I'll keep continuing. This is the topic that is known to you. This is just adding some context. Okay, so basically we have a labeled data set in supervised learning. We split it into training and we split it into test. You're aware of this part. Then we use the training to learn your method. Here you could do SVM or neural network or random forest, whatever your technique of your choice. But then what you do is you choose a method, but that method you cannot use directly until you learn the parameters of the method. So SVM, there are two parameters, cost and gamma. Every neural networks has some parameters like how many neurons to use, how in each layer, and how many layers to use, how many hidden layers. So these kind of choices are made. Then you'd have a learned model, because this is like neural network, but then based on your correct choices of what is more relevant to your training data, you will have a learned neural network model. So this is basically just a function, right? Which has those parameters fixed, so you can predict with it. So now then you predict with it on the test set, and then you have some estimate of test error, because you know the true result, true answers, true responses, or true labels here. So you only feed the input variables, and you see how well your predicted labels are close to the input labels, or how well your predicted response variable is close to the input response variable in the test data set. So these are known as a test error. But then we can zoom in this a little more, because we did cross-validation. That comes in at this phase, from choosing your learning method to getting a learned model. So how you choose your parameters is based on cross-validation. So this is the more zoomed up view. Training set, same thing, I'm zooming up the learning process. So your training set you're taking, but again, you divide it into multiple validation sets. So based on your 5-fold cross-validation or so. And then you learn models. So you learn one model for each choice of parameter. So for say SVM, for cost equal to 1, gamma equal to 1, for cost equal to 1, gamma equal to 5, so on and so forth, all choices. Then you select the best model in terms of the validation set. This is the cross-validation process. Okay, so so that's the overall context to what the workflow is. Now we'll be focusing more on the accuracy estimate, either here or be it inside the cross-validation box in here. How do you validate in your accuracy when you select your model? This is something we focus more on, which is the cross-validation error. But then what we're focusing on in both places is what is the metrics you want to use. There are different kinds of metrics involved, especially in classification problems. In regression, it is straightforward. There is only one metric, your mean square error or root mean square error. That is basically you're subtracting your predicted values from the true values, and you're seeing an average of those errors, or squares of those errors, right? That's the mean square error. It's only one metric, but in classification, there are multiple metrics that come into play. So that is what we are focusing on in today's slide, today's slides, as far as our context goes. So this is in the beginning part of the phase, so we're not focusing more on this. So the question is, how do you partition your data set? We've discussed this before. You do random partitioning into training and test set. So you can do it once, you can do multiple times. So each time it's up to you. If you do it multiple times, even the better. You see how your performance is by training on this and predicting on test. You note down the error, you do it multiple times, you can average that error. There is something called stratified sampling. This is important in cases when you have a highly imbalanced data set. So what does imbalance mean? It means you have a lot more of one kind of a class samples than another class. So say if everything was plus and only 2 were minuses, which means most of your rows are coming from the plus class and very few from negative. Similar to say you have a data set with 1 million data points and a million rows, and say 900,000 are email data that are not spam, and then only 100,000 are spam, then that is highly imbalanced, right? 10% is one record and 90% is another class data records. So in those situations, what happens is your model gets automatically biased towards just like that, predicting for regardless of what your input is, it keeps predicting the majority class, because just by chance it might predict whatever you feed in, it will always say things are not spam, and just by chance 90% of emails are not spam. So it doesn't mean that your model is performing with 90% accuracy. Then because you need to look at how many of not spam emails are really being caught, spam emails are really being caught by your method or your classifier. classifier. So there are multiple metrics involved, and some choices you need to make in your methodology in addition to the metrics. So which is when you're splitting your data into training and test, if you have a highly imbalanced data set, then you can do what is known as a stratified sampling. So what that does is it tries to automatically make sure that the class proportions are maintained in each set in training and test. So here you may have initially very imbalanced, but it will resample in such a way that some records will repeat more times, especially the minority records, the negatives, and it will be more balanced. That's what they're trying to do in stratified sampling. Same thing could be done in stratified cross-validation. The good thing is you don't have to code all this internally. There are a lot of techniques where you can just, in your function, you can literally say stratified equal to true or stratified equal to false based on whether you have labeled or not. So that is why I'm going over that. And then comes the process of tuning in our methodology, right? Once you have a train and test figured out, you take your training data set, then you have to do cross-validation. So this is again a recap. You're dividing your data set into, say, 5 folds. If you're doing 5-fold cross-validation, 5 subsets. So then what you do is each time you leave one subset. So say first time you train on S2, S3, S4, and S5, you test on S1. So next time you drop S2 and you train on S1, S3, S4, and S5 subset. So on. So you do all 5 combinations. You have 5 errors because each time you're predicting on test set and you know what the true predictions are. Well, the true values are like the ground truth and what you're really predicting. So you have 5 errors. You average the results. That is the cross-validation. So something like that. Say 11 by 20 were predicted on this set. This is 1 error. This is 1 accuracy. So you average accuracy is everything averaged up. So it is 73%. But now comes the real question. Since you're always focusing in our talk on, I've been saying that we're focusing our talk on the metrics that we need to use. So we will move towards that part of the process now. So this is, again, the same thing that we were looking at. Okay, so the first metric. So here's where the metric starts. So one metric that is super important and used very popularly is known as the confusion matrix. All this is a very simple thing to understand. So say you had a problem with 10 classes. So this is an activity recognition problem, for example. Say you're building a model that looks at video of people and it needs to say what the person, and it needs to say whether that human being is, what activity is he doing? Is he bending? Is he jumping? Is he skipping? Is he walking? Is he waving in one way? Is he waving in another way? So you're trying to do some computer vision, right? So basically you run a SVM or a neural network or a CNN on your video data, and then it'll automatically try to classify whether the person, what activity the person, human activity the person is doing. So that, say that was the example context, then what you would have in terms of how well you're performing is the follows. You can look at overall accuracy like you did before in the before slide, but you can also look at class by class performance. So you can see, say for example, how many of the running activity were actually classified as running. So basically this is the true actual class. These numbers, these names are the predicted class. So you see here. So here you're seeing how many of the runs were really predicted as runs. So apparently he tried 100 times, he looked at 100 runs, but only 89 were predicted correctly. And he made 11 mistakes. Now, the 11 mistakes could as well have been distributed across other classes, but here it's peculiar that it's interesting that the 11 mistakes were exactly made with respect to this. So it's skipping. So which means the runnings, which were supposed to be runnings, 11 of those were falsely classified by the model as skipping. I can see how these two are kind of similar, right? Running is not as similar as waving, but it is more similar. Yeah, it's not very similar to waving, but it's more similar to skipping, right? So a little more. So that's how the model might have gone inside. And then the jumping, for example, again, jumping and skipping, the model got confused, 11 errors. Waving, there were 2 kinds of wavings that it was trying to model. So wave 1, 67 times it caught correctly, but 33 times it thought it was wave 2. But wave 2 always being caught as wave 2 by the model. So this model is reasonably performing very well as long as this is based on the cross-validation data. Because if it is the test data or training data, you don't know if it is overfitting or underfitting. But if you look at the cross-validated confusion matrix, then you're very sure it's a reasonably good model. It also depends on your business context, right? So if this is some classification problem where you want to make only 1 in a million errors, then this may be bad. But otherwise, it may be good enough. It depends what your business is looking for and what is the maximum. What is the best you could ever do, given your data set is another criteria, another thing to consider, right? Because you may have a very bad data set, then no one can predict more than that. So anyway, this is one kind of a metric, very simple. In the email example, you only have 2 classes, then you would have only a 2x2 confusion matrix. So you will have actual spam, no spam, and then how many were predicted as spam and no spam. So if you see there is a pattern, the bigger the numbers on your diagonal, the better it is your performance, because the diagonals are class 1 was truly predicted as class 1. How many class 2 were truly predicted as class 2? So these are the true predictions. Anything off diagonal elements here or here are basically the errors, and it's also saying what kind of errors it's making. So instead of looking at the overall accuracy, which is also a good metric, you also want to dig deep and dive into how your performance is on a class by class basis. Okay, so this is what the 2 class setting. You would have spam, no spam, spam, no spam, right? So diagonals are the good predictions. How many positives were predicted as positive, negative, negative. The false predictions are the off diagonal, which is the bad prediction. Also, this notation of true positive, false negative, true negative is very popular in clinical studies and in medical fields as well, because say someone is doing a test for, I don't know, HIV. So if your testing mechanism is a good test, it is supposed to classify the positively infected people as positive as much as possible, and then it should never say a positively infected person is negative, which means he's not having HIV, although he has HIV. So then this is this number. Here is the other way around. HIV negative, he doesn't have HIV, and then if you if you truly catch it as not having HIV, that's a good thing. But if you say, well, sorry, this is the actual class. This is all right. So here it changed the notation. So before we had actual and predicted, now he wrote actual and predicted. Same thing. So if he doesn't have HIV actually, and if you predict it as having HIV, then that's a danger as well, because you're just putting this person through a lot of other follow-up activities, although he's not a patient. Right? So basically, if you have a good test for whatever, be it HIV or be it for diabetes or whatever you're testing the medical condition, the better the performance of your test in the medical field, because that's also in a sense a classification problem. You're not running a statistical model or a machine learning model. You're doing it through, I don't know, some hardware or some chip or something, right? Or some blood test or whatever it is. So the bigger the diagonal elements, the better the performance. These are the 2 kinds of errors you can make. One is positive can be falsely classified negative, or negative can be falsely classified positive. So this is the same terminology used both in machine learning as in medical studies, medical experiments. How do you measure accuracy when you have a confusion matrix? All you do is you sum up how many correct values you correctly predicted, so true positive plus true negative, then you divide by all 4, which gives you the total size of your data set, by the way. So which is just the size of the data set. So if you had 100 records and if you did 70 records correctly, in terms of classifying them of whether they are positive or negative, then you'll have 70 by 100, 70% accuracy. Right, now, this is the big question now. Is accuracy an adequate measure? It is a good measure, but it's not the only measure. There are other things involved. There's a trade-off involved. That is a point. So what are the trade-offs, for example? I mentioned it, right? So you might have a high accuracy if you had an imbalanced data set where you had a lot of positive records in your data and very few records were negative, and if you did all positives correctly, then you have a very high accuracy because there is a big chunk of records that are positive and you're predicting positive correctly. But your accuracy within the negative class could be very bad, but that will not show up in your overall accuracy estimate because the data is imbalanced. So out of 1,000 records, say 990 records were positive anyway. So the 10 records, maybe you performed exactly the opposite, right? You did not classify correctly. which means on the negative records, your accuracy was 0 or close to 0. But on your positive records, your accuracy was 100%. But the overall accuracy is also going to be very high. It's going to be 95, 97%, which will falsely make you think that you're always doing good. But you need to understand, because there is a different cost you will pay for both kinds of errors in practice. The error you pay in one situation for having more false positives is very different from the error you pay in your business situation when you have false negatives. It depends on what situation you are in. Even in court of law, right? If the person is actually not a criminal, and if you falsely convict him as being a criminal, then you're making this kind of an error, false positive. You're falsely calling him a negative person, a non-criminal. So there is a different cost you pay in the society for that versus saying the person who is actually a criminal versus saying he's not a criminal. There is a different cost for that, because the criminal is roaming free in the society. But here an innocent is made guilty, right? He's getting the punishment. So different costs. These are not the same thing, but both are important. So you need to look at individual performances on a class-by-class basis. So some of the additional metrics that are important to understand the situations, that the examples I gave you, in addition to accuracy, are the true positive rate and the false positive rate. So it's also known as recall. The true positive rate is basically the TP, this number, how many true positives you did correctly, how many positives were correctly classified as positive, divided by TP plus FN. So divided by the total number of positive classes. So this is like, within the positive classes, what is your true positive rate? So that is a nice thing, right? Then you can also look at true negative rate. Then you will know individual performances. Similarly, false positive rate, right? So how many false positives divided by actual negatives that you got, which is the true negative. So, plus false positive. So this is the total number of negatives. Okay, now since we have multiple metrics, we have TPR, FPR, TNR, FNR, right? So many true positive rates and false positive rates. Then we also have accuracy. Now there's a trade-off involved, because you cannot optimize everything, right? There is no free lunch for anything. You have to pay some cost when you're optimizing for one metric with respect to other metrics. So that is literally visualized and calculated using what is known as an ROC curve. These are very popular metrics in machine learning. Regardless of what technique you're using, people talk about these, because when you fit a model in your company, people care about how is its ROC curve, how is the classification accuracy, how is the TPR, how is the FPR, how is the recall. So these are very common numbers and metrics. So it's the same metrics that any technique is judged against. So say, for example, I was showing, so this is some ROC curve I fit for some model, right? So let's try to interpret it. What is an ROC curve? It is the false positive rate, FPR on the x-axis, and then TPR on the y-axis. Okay, so basically it is saying there is about, I don't know, this is 0.6, this is 0.8, so it's maybe 73% or 72% accuracy, because the true positive rate is high, is the y-axis is high. And then this is at a very low amount of false positives, right? So maybe 4%, 5% false positives. For low amount of false positives, I'm having a good amount of accuracy, right? But again, it is relative. Is this low enough, or do you want it lower? Or maybe you can still be okay with the higher false positive rate. Is this high enough, or do you want 95%? It depends on what problem you're looking at, right? Same thing here. Your y-axis is the false positive rate, x-axis is the true positive rate. Now the question is that as you allow the model to make more false positive decisions, which is a bad thing, obviously its true positive rate also increases, because you're allowing it some room here to make some mistakes, but it's catching the true positives properly. But the tighter you make it here, as you see, your accuracy also starts going down. So there is a trade-off. How much of false positives are you going to allow for in your business? And based on that, you will see how much true positive rate or how much catch you'll be able to get in terms of the positives. So this could be, say, a fraud detection problem. Say, instead of email class, you can say you're having a fraud detection model, right? Fraud classification model. So ideally, say it was your banking company, your credit card or your debit card, your bank company. Ideally, you don't want a company like Bank of America or Wells Fargo, PNC, whatever, Chase Bank, whatever your popular bank is. You don't want the bank to, freeze an account of a good customer. Because it's a very bad decision that the bank is making, right? Not just from a financial perspective in terms of the trouble you're causing the customer, but also in terms of customer satisfaction, right? The customer would be really pissed off if he was a perfect customer having a very legal job and doing proper stuff in the society, and his account gets frozen or something because the bank's classification model thinks based on his data set that he's a fraud, although he's not. So that's a false positive decision. So ideally, most companies in fraud detection would like to have a very low false positive rate because they want to commit very less false positives, maybe 1 in 100 mistakes or maybe 1 in a million mistakes, where an innocent guy is falsely put through all the fraud procedures. But at the same time, it would also like to catch the real fraudsters, which is the y-axis, right? So here you want to be as high as possible on the curve, right? Because ideally, you want to catch, if there were 1,000 fraudsters, you want to catch all 1,000 of them or 999 of them as high as possible. So you want to catch the most number of fraudsters and minimize the number of mistakes you're making where you're calling an innocent person a fraudster. So this is the trade-off between the TPR and FPR, right? Same thing with respect to spam or no spam, right? Because you might as well have sent a very important email that might have ended up in the spam folder if the Gmail spam classification was not very high accurate. So then that's a false positive, right? A good email is being falsely classified in the spam folder, and your receiver, however important your email might be, might not even look at it. He might have as well just deleted his spam folder. Like just select all and delete, and your email is out in trash. So ideally, even in spam, right, you want to keep a low false positive rate of performance, but a high TPR. But there's a trade-off. You can't get the best of both worlds always, right? So as you see, as you keep allowing for more false positive mistakes, only then your TPR is increasing at a different rate. So the question is, are we okay with this amount of accuracy since this much we are only causing this amount of false positives? So that is a business question, right? At what threshold do you want to operate? And another question is, one might think is, if you have one model, once you predict, you only have one bunch of numbers, right? You're populating this 2x2 confusion matrix or your 10x10 confusion matrix here, right? Depending on how many classes your model is predicting. Once you have made it, you only have one set of numbers, right? You have one TPR, one FPR, one accuracy value. And people might ask, if you only have one TPR and one FPR, how are you getting complete curve? Because then only you have one point, right? At one particular FPR, in my confusion matrix, I have one particular TPR. How come can you plot all these numbers? So then what this is going on here is the following. Here, as we said, every technique has some internal parameters. Most techniques basically do not predict 0 or 1 directly. Let me draw this. Any questions? Feel free to interrupt. Okay, so yeah, so your technique or your model, there is something called hard classification, soft classification. Most models are soft classification. So data goes in, right? So you're basically X and Y. Your data goes in, your model throws out. There's a lot of process going on, cross validation, everything, but I'm doing a very overall process. In hard classification, it automatically predicts either 0 or 1 if it's a binary classification, right? There's no spam or no fraud, whatever your context is. No disease detected. But in soft classification, which is what most popular models do, you are always predicting a probability between 0 and 1. You're not predicting one number, or you're not explicitly saying it is class 0 or class 1. You're saying some numbers, and it is a probability. So if it is 0.90 for some record, then it is more closer to 1, then you can say it is more likely class 1. If some record is 0.2, then more likely 0. 0.1, more likely 0. Something is 0.5, then you're in a soup. You don't know if it's class 0 or class 1, right? Whatever your rule decides. But anyway, but there is more uncertainty involved. So each record, it will not predict 0 or 1, which is what you finally want, but it will predict something like this. And based on that, you need to convert your probability into a decision of whether it is explicitly 0 or explicitly 1. Here you have any number between 0 and 1, here then you add 0, 1. Then you have your final prediction, right? Classification done. So now, how do you make this threshold, right? So maybe 0.5 could be one threshold, for example. Say, if any probability that your model predicts above 0.5, then I will call it class 1. If it is below 0.5, greater than 0.5, class 1. If it is less than 0.5, then I will say it's class 0. Right? But then the question is, once you fix a threshold, then you have one classification model that is explicitly classifying, then you have one confusion matrix here, right? But then if you choose a different threshold, if you choose a different threshold, say 0.4 was your threshold, then anything greater than 0.4 class 1, less than 0.4 class 1, you would have another confusion matrix for that kind of a model, different performance, right? Every time you're predicting it differently. Now the question is, if you have multiple, each threshold will give you one confusion matrix. So each threshold will give you a different TPR and FPR, right? So basically then you can plot your entire ROC curve for all possible thresholds between 0 and 1. So for different thresholds, you know, you have a different confusion matrix for your prediction, right? So for each threshold, you have a specific TPR, FPR, another threshold, another TPR, FPR. Then you can plot all your TPRs versus FPR. Then you will know at what the trade-off is looking like in your situation, right? Say it is looking like the red curve, for example. Then you know, based on business decisions, at what FPR you want to operate or at what TPR you want to operate. Some people are okay with making a lot of FPRs in some contexts, in some businesses. Then they are more conscious about high TPR. And then they say, I want to operate at TPR of 85% or 95%. I'm okay if I make 60% FPR. But in like the fraud or the spam kind of a thing, people want to operate low FPR. Then people will usually then fix not the TPR, but then they'll say my constraint is I want to fix the FPR to be less than 5%, 1% or 10%. And based on that, you know what TPR you will get for your model. So at least you have the entire curve, then you can make your decision. You know what your trade-offs are. So you will decide what is your constraint. Do you want to fix your TPR and then choose what FPR you can get? Or do you want to fix your FPR to be as low as possible and then take whatever TPR it will give you? So either way, and then once you make that decision, then you know what threshold is giving you that particular confusion matrix. So then you will say, okay, I want that particular threshold because I want to operate at TPR of 65% and FPR of less than 1%, right? Less than 1% possible. Then maybe the threshold is not 0.5 that corresponds to that ROC number trade-off. Maybe it is 0.7 or maybe it's 0.3, whatever it is. Based on that, you choose your threshold, then you have your final one. So this is the ROC metric. So this is a ROC curve example from a true data set now. This was like a cartoon, is a true one. So he ran some 3 techniques on some classification problem in bioinformatics on data set from some journal. Anyway, but it was a classification problem. So he ran 3 techniques: BaseNet, naive Bayes. Naive Bayes, if you remember, this was the first thing we did in our first or second slides, lessons. So naive Bayes is a very basic technique, right? Then the Bayes network, then he used a C5. This is a decision tree. C5 is a very old decision tree. So it's much older than random forest. Okay, so then each technique has its own ROC curve. Now the question is, you're not only comparing what TPR and FPR trade-off you're looking at in each curve, but you're also looking at what is the different trade-offs you're getting with different techniques, right? So say, let us look at this. Say at 20% FPR, the dark line, so BaseNet is doing better than naive Bayes. At 0%, so from 0% everything is same, but you don't want to, you'll never have 0% FPR because then your TPR is very low. So say once your FPR is slightly higher, from here, always your BaseNet, is the top line, is doing much better than these other 2 lines, right? By the way, since you want to have a high TPR for as low FPR as possible, from a calculus standpoint, what happens is the higher the curve it is, the better it is for you, because the closer it is towards 0 on the x-axis and higher on the y-axis, it means you're getting a high TPR for a very low FPR. It's a good thing. So basically another way to say is the greater the area under the curve, the better is your ROC, right? So if you see the area under the top curve is much higher than the area under these points. So that is how you interpret it from a practical standpoint. Now, say for the most part, until 40% FPR, your BaseNet is dominating, is doing much better. Whatever FPR you want to choose, your BaseNet is giving you better TPR at the same FPR, right? So it's a much better technique. But then say if you're in a business where you're okay with 45% FPR or 40% FPR, then if you see all techniques are having the same amount of TPR, there is no additional gain, especially between these two techniques, BaseNet and naive Bayes. C5 is always, malperforming, is always bad. So out of these two techniques, then BaseNet, naive Bayes. Now BaseNet is a more complicated technique. It's harder to train. It's more data and computationally intensive, more time taking. Naive Bayes is super simple. It's like a simple calculator kind of operations. So then people might say, hey, you're in a business where you're okay with 45% FPR. That's where you want to operate. But then both are performing the same TPR. So then why choose a very complicated technique like BaseNet? It's a headache for you to maintain and retrain your model every month. Let's just stick to super simple technique, naive Bayes. It'll run in a moment of time. It's super easy to maintain. So then people may say, okay, since the performance is the same at 45% FPR, I will go with a simpler technique, computation. But if you're at a business where you want to operate at less than 5% or 20% FPR, then by all means, your BaseNet will do much, much better in terms of capturing more TPR. So this is like a real life example of the ROC, right? So this is, the slide is talking about the same things. So how do you create ROC curve? I just showed this in this cartoon here, which was about the threshold. That's what it is saying. Sort your predictions according to confidence, which means between 0 and 1, you have a probability. Then locate a threshold, and for each threshold, you compute a TPR, FPR, you plot it. So you do that again and again for all thresholds. So from high to low confidence or high to low probability. Then you have your ROC curve. So that is how you're plotting it. Okay. Now, at the same time, since the ROC is a plot of TPR or FPR, there is also another curve called the precision recall curve, which is another trade-off. See, there are so many metrics involved. It's not just accuracy. There is TP, FP, so many things, right? ROC. So another popular curve is known as the precision recall curve, which is the recall rate versus the precision rate, these two fractions. So even there's a trade-off. You cannot get the best of both worlds. If you want high recall, you'll have low precision. But the question is, what trade-off you want to operate at? Again, this curve is changing because you're plotting it for different thresholds. This is again an ROC curve, mammography, which is like you're trying to do a mammography test and try to run a model to classify whether, looking at the medical images, whether it is breast cancer or no breast cancer, right? So ideally, you don't want to miss a cancer lady has been a woman as not having cancer, then that's a false negative decision that has a grave consequence, because it could have been in an earlier stage where you could have given the treatment and the woman would have perfectly survived and be healthy in the future. So you don't want to make those mistakes, right? In this situation, there's a different cost you're paying for each error. Versus, say, calling a person who is not a breast cancer patient as being a breast cancer patient, there is another kind of cost because you're causing her a lot of aggravation and tension, because she might be thinking she has cancer, although the reality she does not. So there's a ROC of two different models that classify by looking at mammography images, the scan images. So you can perform a different trade-offs. So then in a cancer classification scenario what FPR or TPR, FNR, TNR you want to operate at. In some other thing what you want to operate at. That's a business decision. Based on that you decide which model and at what trade-off of threshold you operate at. This is the precision recall curve, similar to the ROC curve for the mammography. So these are like real data sets and real curves as you see, right? It's not like this. This is like a cartoon. Okay, now the question is, if you have a test set, then I know how to generate a confusion matrix on a test set for any given threshold, then I know how to plot TPR versus FPR, because these are just fractions I compute. But then the question is, what about cross-validation set? There are two ways to do it, but I like the other one of those more. Both are okay. Let me show you. You're taking you to the right slide. So in cross-validation, you're dividing into different folds and each time you're dropping one fold and you're testing on it. You're training on the rest, right? This is what cross-validation is. So here you have one ROC curve. Here you have one ROC curve, one ROC curve, one ROC, one ROC. You average all the 5 ROC curves. Right? Because every time you have a prediction, you have a confusion. So So that is how you do a cross-validation based ROC curve. You see, that's what he's writing. How do we get ROC or PR curve when we do cross-validation? So plot the average curve. This is the approach 2. Yeah, this is like a summary slide of what we did. And this is a future topic. This is hypothesis testing. This thing we'll be covering in our next in the coming up lessons. So now the thing is, you know SVMs and neural networks now. So now you can generate ROC curves on SVM or neural network. Say the ROC that I show in the future for random forest. This ROC was for random forest model actually. I had on my computer. Anyway, so the overall point is these metrics: ROC, confusion matrices, TPR, FPR, TNR, FNR. These are standard metrics, regardless of whether you do SVM project or neural network project or random forest project or something else in the future, deep learning, whatever your new classical technique is. So in the coming lesson, what we'll do is we will cover another technique because we covered SVM and NN, we will be covering random forests. Then you have like enough pipeline to do projects on your own, right? Like say Chun already started doing it, is great. You can choose your data sets online, and then you can run all the 3 techniques and generate 3 ROC curves and plot this something like this, right? Here he has 2 techniques, you can have 3 techniques, right? For your chosen data set, it could be something else, may not be mammography, but you will have 3 curves and you will know what the trade-off is between SVM and random forest and neural networks on that particular data set. These kind of things. Yeah, you can. This will literally go into your resume. You can write, right? You did a classification model or fraud detector or something else that you chose. And then you say you computed the ROCs, you did cross-validation, you did with neural networks. You can have all these bullet points. You did random forest, support what you mentioned. It will give you a lot of a full-fledged end-to-end machine learning, like supervised machine learning project for your resume. So it's all up to you on how much you would be running these and how much you will really dig deep into it. As far as R goes, it is super easy. There is a package called ROCR. This is the R package. It's as simple as just 1 or 2 function calls. It will do the plots and everything for you. All you need to do is finish your cross-validation and have your cross-validated model. You pass that. Then you have predictions. If you pass the predictions and the ground truth and choose what metric you want, it will do it for you. I might have some example from some scratch pad. There won't be clean code, but I might Okay. Look at this code. These 4 lines will give me just these 3 lines will give me the ROC curve. The prediction, performance, are the 2 functions from the ROCR package. So I'm passing the score that my model is predicting. The score means just the probability between 0 and 1, what are the model is predicting, and then I'm passing what the ground truth or what class it is for each row. For each row I have a score, the model is predicting, and what the ground truth is. I just pass those 2 arguments, those 2 arrays. Then I save it. And then I run the performance function. And then here I can choose even more. Here I'm choosing I want only TPR and FPR, and then I'm plotting it. But I can choose whatever metrics I want. I can choose TNR, FNR, right? And then just these, as simple, just 3 lines of code will give you the ROC. So it's not as understanding how to interpret it, what is going on is all we are doing in the slide. But when you run your project, it shouldn't be that daunting a task. It might look like fancy plots, but when you're running it, it's super easy. And then now you know how to interpret it. So once you have the error, you can also interpret it. Similar thing in scikit-learn in Python, your ROC curve is super easy as well. ROC, you will have super easy examples like just 1 or 2 function lines or functions. Here it's only 1 function call, right? ROC is score. True prediction versus here is the other order, right? First we passed in other order in R, here in Python the other way around. So first he's asking ground truth, then he's asking your predicted score. And then you can choose whatever metrics you want to calculate, and then you'll get the ROC curve. So it's just 1 function call, as simple as that. There is nothing. There's no like algorithms or data structures that you need to code to get this done. It's just a function. Yeah.
What type of data set should we use for RLC?
Any classification problem. Any classification problem. The data set is up to you, right? You can say, find a data set from the UCI machine learning repository if you want. Or if you had some data set in mind, well and good. So, say you did dual data set. So ROC is not a technique, by the way, Raghu. It is just a way to evaluate your classification technique. So
Okay.
anytime you're having a classification problem, you have an ROC curve.
Okay, because you gave the examples of criminal and HIV positive, that kind of example, that I thought it's particularly for a few situations for like.
No. Any classification, because HIV is also classification, right? You have two classes.
Yeah.
Two classes, only two possible. He's really infected or he's not infected.
Okay.
Yeah, so it's a classification problem. Your model needs to decide. The model could be a doctor, a human, or your classification model, right? Whatever it is. So any classification problem. It's not for regression. We only study regression classification, by the way, in this course till now, right? So classification problem. So you can choose any classification data set. Right. So say there is a data set for lung cancer, right? You need to classify cancer, yes or no, by looking at whatever that medical data is. There is letter recognition. You want to look at images and say what letter it is. Is it A? Is it letter Z? The model should automatically say. Yeah. Anyway, this has a 304 data sets, so you can choose whatever data set you want. This is activity recognition. This is another example, right? You're looking at the person's video or some data or some sensor data from his smartwatch or whatever, and you want to say whether the person is running, sleeping, is alive or dead, whatever it is. Yeah. There is an Amazon Commerce review data set. So many. So that brings us to the end of the class portion of the day today. Any other questions? Cool. So, yeah.
No other questions. Yeah.
Oh, you said another or no other?
No other.
Oh, no other. Okay, yeah. All right, cool. So, all right. So have a good weekend. Try to continue. Everyone, I think, try to start doing some project, because taking this course, just writing this is not good enough, right? It's just the fact that you took a course. A lot of people take a lot of courses online. So what you want to do is convert it into projects, assignments, small. It could be a 1 bullet point, could be a project with 3 bullet points, whatever it is. Convert it into some work where you're converting your learning into some piece of code that does some task, some classification or regression problem on some popular data set, and write it in your resume. That's how you can add these things more and more. You may be applying for a data scientist role, or you may be trying to apply for a business intelligence engineer role, a data analyst role, whatever the role is. Having projects is always a good thing, as far it is directly or indirectly relevant. If it is completely irrelevant, then I get it. If you're doing some mechanical engineering project and you're applying for a BI engineer or a data science job, then maybe relevant. Or if you're applying for a data science job in Boeing, then maybe it is relevant if you're doing a mechanical engineering based data science project. So it depends. So you might want to really do this. You take more, initiative on your own side, and this is something you are supposed to do hands-on. I'm there only to guide you. You can ask me if you get stuck or what to do or stuff like that, what direction to take, but then you're the one who does it and writes it in your resume. Feel free to get into that initiative. Now is a good phase. You've covered a few techniques, so try to do an SVM project or a neural network project or random forest project where you cross-validate, you generate the errors, you generate ROC curve, and then you write it down. All right, so have a good one. Good weekend. See ya. Bye-bye.
Thank you.
Sure.